Any questions over here? Like I said, if you have any issues seeing anything on the screen as I'm writing, just let me know. One of the things that does help with this is that if there's something before that you want to go back to, I can always scroll down rather than unerase the board. It's a little harder. So were we okay with how we got the system of equations set up last time? Any issues with that at all? In this particular one, this would be our matrix that I believe that we're row reducing if I just order it from F1 to F5. So we use our calculator to get that taken care of. This isn't going to be on the recording because I don't have the camera hooked up to the computer, the Surface, but that's okay. So we'll type in our matrix into our calculator here. We've got a 4x6, it looks like here. So let's just get these things entered. Oops, -1. And hopefully I'm not going too fast where I've made any errors as I'm typing along. All right. So go in here and get our reduced row echelon form for A. And it row reduces to, oops, maybe, yeah, we'll back up the laptop. So this, when we put it into reduced row echelon form, went to 1, 0, -1, 0, -1, -10, 0, 1, 1, 0, 1, 60, 0, 0, 0, 1, 1, 50, and 0, 0, 0, 0, 0, 0. I went through the calculator quickly, but I hope we're all on the same page of being able to get the things entered in the calculator and the reduced row echelon form. Then we'll be able to interpret the answers of what's going on with a particular application. That was weird. But Microsoft respects my privacy, and maybe it shouldn't minimize the stuff on my screen. What this is. Must have bumped something on the pen, and so I decided to open something else up. Sorry about that. All right. So the last row where we have the row of zeros, that's telling us that it's still consistent, right? There's no issues with inconsistency here because we have a row of zeros. The last row tells us that 0 equals 0, so there's no issues with the system being inconsistent. However, we do notice that we get infinitely many solutions here because we certainly have only 3 rows that have pivots in them. So I can only solve for x1, x2, and f1, f2, and f4 here, right? Those are the columns that have the pivots. So we can only solve for f1, f2, f4. f3 is free, f5 is free. You agree? So how do we handle the free variables again? Forgot to put my watch on Do Not Disturb. How do we handle the free variables again? What do we write them as? Parameters, right? So what do we want to use? S and T, doesn't really matter, right? I'll let the F3 be S, the F5 be T. Those are the ones where we don't have pivots in those columns. Okay. I guess I should ask if everybody got the same row reduced matrix in case I type something in incorrectly. But all right. So then we can write the other ones in terms of the parameters, right? Okay. So in particular, how would we write F4? Yeah, 50 minus t. Because we're going to subtract, we would put the t in for the F5, right? And subtract it over to the other side to solve for the F4. So we get 50 minus t there. What about the F2? Pardon me. Good. We put the S in for the F3, put the T in for the F5, and subtract it over to the other side. So you'd have 60 minus S minus T. And for the F1, yeah, S plus T minus 10, or yeah, I'll write it the other way just to keep it consistent with, whoa, hey. Keep it consistent with the other way we wrote the other ones. This gives us the infinitely many solutions to the system that we solve, but since we're doing an application problem, we probably want to try to make sense of what the answers are, because maybe not all infinitely many solutions make sense in the context of the problem. In particular, if the flows really are going in the directions that they say they're going in out of those nodes, then we want to make sure that those flows are positive, right? Okay. So let's see if we make sense of all of those things. Well, certainly if the flows are going to be positive, these conditions here tell us that S and T both better be positive, right? Let's work our ways. We'll come at the simplest one of the three left. What does this tell you about T? If we want to make sure that all the flows are non-negative, I should say non-negative rather than positive, it doesn't matter. What is it? Yeah, it'd be less than or equal to 50, right? So using the fact that T has to be positive, and this one needs, the flow here needs to be positive, we need our T will be between 0 and 50, right? So that's one condition that we would have on this. Looking at F2, what does that say about the what needs to happen with the S and the T? Yeah, the S plus T better be less than 60, right? Because we want to subtract too much off. If we go up a row, if you will, go up to F1 now, what else has to be true about S plus T? It needs to be at least 10, right? We agree with that? And again, one thing else that I didn't write was that our S needs to be positive. So I'll write that above here. Oh, I said positive and I wrote 10. What am I doing? Sorry about that. That's probably about as good as you can get on the conditions, because even though this has to be at least 10, I can't say that my S has to be at least 10, because it's entirely possible that my T could have been 10 and the S could be 0. Right? I can't just say plug in 0 for T here and say, oh, the S has to be at least 10. I don't know that necessarily because the T could be bigger. It's about as good as we can get for conditions. But we know that if we're looking at all of the flows being positive, then those are the conditions that we would have to have be met on the S and the T, assuming they're positive. If you interpret a negative flow as just the flow goes in the opposite direction, then there wouldn't be any need to do this. Yes.
So S can be equal to 0. That's okay.
S could be 0 as long as T is at least 10. No, that's okay.
Oh, well, yeah.
Yeah. The only way that S could be 0 is if T is at least 10. Yeah. But yeah, it is possible that S could be 0 in that case. If you wanted to, you could draw a picture of kind of the feasible region of what has to happen. Or if you could draw the set of points where it would work.
It's impossible for S to be 0. Right?
Is it? Yeah. Yeah, we can make S 0. As long as the T is 10, S could be 0.
And max T can be 50.
0 plus. Oh, I think it's right. Never mind.
Yeah. I mean, if we were, like I said, if we were to draw a picture here, since I have a two-dimensional region, I could draw a picture. Let's say this is my s-axis, this is my t-axis. The highest my t can be is 50. My s is positive, so I'll be on this side. My t is also positive, so I'll be in the first quadrant over here. Oh, you can kind of see that I'm drawing, scribbling around there. I didn't know if I'm doing this, I didn't know if you could actually see what I was doing with that. It's kind of hard to see. All right, but then if I look at the other lines, I would have s plus t is 10 would be the line that goes this way that intersects the axes at 10, right? Yeah. And then s plus t equals 60 would be the line that goes that way. T can be at most 50, so I'd have that line that would cut it off there. And then I would, didn't I just draw a line? We cut it off there. I thought I just drew a line and it was gone.
You did. You like drew it and immediately
That was weird. Okay. And then so it'd be anything in this region works for the S and the T. In that case, is what we're saying. So yeah, S can be 0 as long as your T is between 0 and 50. T can be 0 as long as your S is between 10 and 60. So I guess at this point, this does give you a cap on the S. The biggest the S could get is 60. If my S is bigger than 60, that would make my T be negative. So it would also give you an upper cap on your S. But this would give you, in it's referred to as linear programming, this would give you what's referred to as a feasibility region. This is where your answer would have to be in. We're not going to do any linear programming, but linear programming is very important in doing optimization things. So anyway, is this okay? Getting the bigger thing is getting the system of equations set up. Is that okay? All right. So as long as you get the system of equations set up and solved, that's the important thing. The same kind of concept works in the applications to electrical networks. We just have to know a little bit about electronics, if you will, to help us out. So let's just look at the first problem here, and I'll describe the diagram, and then we'll get the system set up. So again, I won't have this on the recording, but let's just look at the first problem here that's in that packet that I gave you last time. So much like flows that we just say, if we think about pipes in the previous example, much like what we had in the previous example, we can look at the different nodes and match up what the flows have to be. If you've got electrical currents running through wires, we have the same kind of properties at the nodes. That anything going in has to equal anything going out. That was how we set up the system of equations last time, right? So if I look, they've got the currents mapped on here for you. So the I1 is the one that's going from this node to this node. These aren't nodes here, it's just going around this way, even though it's squared off, it's a round wire, if you will. Okay. So I1 goes from this node around this way to this one. I2 goes just across that one. And then I3 goes that way at the bottom. That makes sense? Okay. So if we were going to make just equations at the nodes, what would the equations be that we get out of that? So again, I'll try to redraw the picture here. Badly, apparently. This one's I'll just do it this way. We'll talk about what that means here in a second. If you've done any electronics at all, you know what that means, but we'll talk about what it means in a second. I'm not going to be overly worried about the physics part of these things here. I forgot to put the batteries in. Okay. We'll get to those other pieces. Just concentrating on the nodes right this second. So again, the I1 is the one that's going around the top, the I2 is going from right to left in the middle, and the I3 is the one that's going around the bottom. Just at the nodes, there's two nodes here. What equations would you get from the nodes? If I look at this left node here, what equation do we get? What the heck?
Is that is this the thing where you circle it and then tap it, it vanishes like
Yeah, me. I've never had this problem with using it before. I used this yesterday in class and it didn't do it. Yeah. So what equation do we get out of this one? Okay, you're right. I'm going to write it this way. Remember that we have to have in equals out, right? I1 comes out, I2 and I3 together are going in. So we would have I1 equals I2 plus I3, right? Whatever goes in, it has to come out, or whatever out goes out has to come in. It has to be matched equally. What about the right node? Yeah, it looks like exactly the opposite, right? This out is I2 plus I3, and then the I1's coming in. It gives you the exact same equation, doesn't it? I1 goes in, I2 and I3 are coming out of that one. So I'm not going to bother writing it again because the right node gives you the exact same information as the left. Okay. All right. So now the rest of the equations that we're going to get are based off of looking at circuits and something called Kirchhoff's law. So let me tell you a little bit about, and my knowledge of the physics behind this is limited, so we're going to do as much as to get the equations set up, and that's what I'm worried about. Want to know more physics? Go take physics classes. That's what they're there for. Okay. All right. So this, when you have the big line and the small line, that's a symbol for a battery. Okay. The big line, if I remember correctly, the big line is the positive, the small line is the negative. There's a gap in here, so you're flowing around this way. But basically, the current would go from the positive to the negative, so it would flow around that way. Honestly, as long as you are consistent with how the things are going, as you're reading around the diagram, you're fine. As long as you know that going this way is a voltage gain. You go from the positive, the negative will cross the positive. If I went backwards across it, it would end up being a negative voltage. All right. These little squiggly lines here are resistors, and those cause voltage drops. It's holding the current back, is what a resistor does. And the voltage drop is equal to the current through the resistor times the resistance. V equals IR is what's known as Kirchhoff's law. Okay? So in this particular problem, they wrote down that this is a 6 ohm resistor. This is a 4 ohm resistor. And this is a 2 ohm resistor. This is a 20 volt battery. And this is a 10 volt battery. Oh, they have the lines going the other direction, don't they? This is the longer line here. Seriously? I must be bumping something at the bottom. I might just be. I wonder if I can get rid of this little menu. I don't know. Well, now I've got something else going on. Anyway, just make this go away. There we go. I must be bumping that with my hand. I'm guessing is what I'm doing. I'm hitting the undo button. That's my guess. Let's move that out of the way. All right. So when we do this, we're going to pick a direction that we're going to go around the circuit. Doesn't matter which way direction you go, as long as you know that as you set up your equation, you know which way the voltage is supposed to go if it's positive or negative. Okay. All right. So usually, I know they have it a little bit different set up in here, but usually they'll just put a. Now I've got a red line in here for some reason. I just go back to what I was doing. Why am I drawing on that picture?
What?
That was weird. Okay. All right. So usually, and I don't, it's not on this particular picture, but usually we'll just draw a little circular thing that tells you which way you're going around the diagram to add up everything. Right? It literally doesn't matter as long as you're making sure that you're adding things up correctly. Okay? In particular, if I went the other direction, my current would be going backward because you're working against it, right? So this one, it doesn't matter. They've got the vertical line drawing down in the picture, so I'll just say we're going to go the same way this way. All right. And so the law that we're going to use is that the sum of the voltage drops has to equal what the voltage gain is from the battery. Okay? That's the way that it works. So here, as I go around the circuit this direction, I hit this voltage drop, and the voltage drop is whatever the resistance is times the current, right? So we would hit 6I1 for the first one. Coming around this way, we're still going in the right direction for the current, right? What would the voltage drop be there? 4I2, and we'll add that. And that's the last voltage drop that we have. And this orientation that we have going around the clockwise is the going from positive to negative around, right? So that should equal the voltage gain, which is 20. Does that make sense? And again, if you've seen the physics and seen the electronics, then you already know how to do this, I'm guessing. So if I screw something up, I'm going to let you correct me as we go along. All right. What about the next one? If I look at the I2, notice that the way I have this drawn, we're going against the current, right? So what am I going to represent that with if I'm going against the current? You know, the minus 4I2, right? Come down to this one, I'm going with the current, it'll be plus I3, 2I3, right? So we'll have negative 4I2 plus 2I3. And now notice that the way this is drawn, this is the negative terminal, this is the positive terminal. The flow is going backwards across the battery, right? It's going from negative to positive instead of the other way around, right? Because the other way, the first one we went this way, didn't we? And that was the positive 20. This way we're going this way, it's going to be negative 10. We're going backwards across the battery.
I'm sorry, I'm confused.
Hmm?
With the 20-volt one, we're going from the small one to the big one, yeah?
Are we going the same way? No. Oh, well then never mind. Oh yeah, we are going the same way. My bad. This is positive 10. Sorry. If you were going the other way, it would have been negative 10. That's my apology. I was thinking about it backward. That's a positive 10. You're right. If we would have set the orientation the other way, it would have been negative because you would have been positive. That would have been jumping backward across. Yeah, you're back. Your current definitely is going from this way to that way, so that's the right direction. Sorry about that. That's okay. And now we've got a system of equations to set up. This one we actually have 3 equations and 3 unknowns, so hopefully we get an exact solution. All right. Unlike the other flow problem we did, we had infinitely many. Let's see if we get an exact solution here. First thing I need to do, Ben already did this earlier, had moved it over all to one side, or we've got all the variables on one side and the constant on the other before we put it in our matrix, right? So what's our matrix, augmented matrix going to look like in this case? Yep. In the second row? Good? Good. We okay with that? All right. So this one now we should be able to put in our calculators, because I expect you to do these on your calculator. I don't expect you to do this row reduction by hand, especially as the circuits get bigger. So we give a 3 by 4 here. -1, -1, 0, 6, 4, 0, 20, -4, 2, 10. Typed all that in and row reduced it. And I did that quickly. If I want to see fractions rather than decimals, just because it's shorter to write, I can tell it to convert everything to decimals here. So let me flip over. I'll write it down. By the way, this is what I want you to do. After, like I said, I'm going to expect you to know how to row reduce by hand. But generally speaking, when you're solving problems going forward, I want you to use the technology. I don't want you to spend hours doing the same type of row reduction over and over and over and over and over again. Once you know what the process is, there's no point in continuing to do it over and over and over and over again, because it's exactly the same every single time, right? That's what the algorithm tells you to do. Yes?
It just appears at the absolute worst way you could possibly do it.
What do you mean?
If I'm reading this right, can you just get x2 is equal to 5, x3 is equal to like, I think it's 5, and x1 is equal to, can't do that math in my head actually.
Well, that must not be the solution, because this has an exact solution, so that must not be the...
Dang, okay.
Because if my x2 is 5, that would tell me my x2 is 5.
Oh, that's a 6, not a 0. I'm sorry.
Yeah, that's a 6. Yep. Yeah, that's a 6. Yep. That's probably what the issue is. So this is telling us that our I1 is equal to 40 over 11. The I2 is actually -5 over 11. And the I3, bless you, is 45 over 11. What does a negative mean in terms of the current here? It's flowing the other way. Yeah, they put the arrow going to the left, right to left. It's actually going right, left to right. That's all the negative sign means here. So it's relative to the orientation that we use. Because remember, right here, we said we went around this way, right? We're going. I know I'm pointing at things on the screen that aren't very large. We went around that way, all right? And notice that's working against the I2, but the I2 is actually going in that direction. So the reason why it was negative is because the arrow was pointed the wrong way on the diagram, essentially. Does that make sense? Let's see if we can get one more set up. We won't spend the time, because I'm assuming that once we get it set up, you can type it in your calculator. Okay. So let's see if we get one more set up and make sure that we're all on the same page with getting it set up. Let's just look at the one right next door, the 1.5.3. Again, I know it's not going to be on the recording, but people can go look at the 1.5.3 on the handout. Actually get it. Okay, so again, we want to look at making the equations here. The first thing we should, well, it doesn't have to be the first thing. It doesn't matter what orientation we use. Pardon me. It doesn't matter what orientation we use. If we use the nodes, we should be able to get the equations out of this, right? For the nodes. And then we'll go back and do the orientations. Okay. All right. So switch back over here. Looking at the node that's at the top left, I'm pointing at it on the paper like you can see it. The one that's on the top left, the one what equation would you get out of that one? I'll go back over the picture. If I go look at the top left one here, what equation would you get? Apparently a silent one. People are writing things, but they're not saying anything.
I1 equals 2 plus 3.
Yeah, the I1 equals the I2 plus the I3, right? Because we got the out has to equal the in again. Right? The I1's coming out, the I2 and the I3 are going in. Okay. How about the one right next door, the one to the right? Yeah, the I6 is I5 plus I3. Right? Again, just doing out and in, right? Setting them equal to each other. Bottom left. So what's coming in? The I1's coming in, and then I2 and I4 are going out. Yep. So I1 equals I2 plus I4. Finally, the one on the right here.
I4 plus I5.
Good. And again, those are just equating outs and ins, right? Just like what we did with the flow problems of the pipes. There's nothing different about that. Okay. Now let's go around the circuits and make our equations looking at voltage gains and voltage drops, right? So they've got the battery set up for you. We'll just use the orientation where they've got the batteries pointed for us for that first one on the left. So we'll go around it counterclockwise. What voltage drop do you have if I go around counterclockwise this way, what voltage drop do you have? 10I1, right? Going around this way. Yeah? That's the only resistor we have. Do you agree? What voltage gains how much voltage gain do we have when we go around? Yeah, they've got this one and that one, right? So there's 20. So our 10I1 will be 20, which makes I1 really easy to solve for, but we're just setting up the equations, yeah? This one doesn't really matter. I'll go around counterclockwise again, just because I went around counterclockwise with the other one. Just for argument's sake. If I go counterclockwise, what voltage drops do you have? You got 20I3, and that's positive because we're going in that direction, right? And the other one's going to be 10I4. So we'll add those two together. 20I3, and I'll switch back over to the screen here in a second where I'm writing these down. 20I3 plus 10I4. We're going in the right direction. How about voltage gains? Well, notice when we go across this one, it's negative, right? And we go across this one, it's positive. So your voltage gain is actually 0, right? And since we've gone counterclockwise each time, let's do counterclockwise around the other one. It doesn't matter if you go clockwise, by the way, just all your signs would be backward. Okay? Your signs would just be the opposite of what we were doing. Counterclockwise, voltage drop. 20I6, and it is positive because it's going in the direction of the current, right? So we'll have a 20I6 voltage gain, 20 and -5, right? Because we're going backwards across the battery. So the voltage gain will be 15. So if I switch back over to the computer here, there should be 7 equations we got out of that, right? We had 4 nodes and 3 circuits in those nodes. We should have enough, hopefully we have enough information to solve everything now, because now we have actually an overdetermined system, don't we? Now, it shouldn't matter if you have overdetermined. The reason why it shouldn't matter is because even if you have overdetermined, you should get a row of zeros at the bottom, or how many rows of zeros you need to make your matrix square. You should get an exact solution out of each of these if you're doing them right. By the way, just as another thing, you could actually use any circuit that you wanted to. Any circuit that you wanted to get an equation. So what I mean by that is, if I switch back over real quick to the picture, you could have, there's 3 other circuits you could have used. You could have gone around that circuit and ignored the middle piece. You could have gone around this circuit and ignored that middle piece. You could have gone around the whole big circuit and ignored the 2 middle pieces and got equations. Any of those would work. They're still circuits, so they would all give you still equations. Okay. So I chose the middle ones here because you can see those more easily. But again, you could go around these 2 and ignore that. You go around those 2 and ignore that. Go around the whole big thing and ignore the 2 in the middle. And all those would work. Yes.
What do you have to do for a given circuit, or is that just not something easily figured out?
You have to do, since we have 6 currents, we have to do having at least 6 equations. Unfortunately, you might get 2 equations that give you the exact same information, like we had here with the 2 nodes. So you make sure that you have enough information, because if you only get 6 equations and you row reduce and you get a row of zeros, you're going to infinitely many solutions. So you need to get another equation to throw in there. So usually, if you pick the right 6, if you pick the right 6, then it'll be fine. But sometimes you get redundant information. I think that's why you get the row of zeros, because you have redundant information in there. But at this point, I hope you're all comfortable with putting that into a calculator, right? Setting it up and just throwing it in there and let it row reduce. I would never ever make you row reduce a 6x7 matrix. That's just crazy. I mean, unless you're looking for some fun on a Saturday night, but.
Do you, when you're making the equations, do you always choose the current that's closest to the resistor to like multiply that?
You always go with the current that's going through the resistor. So this resistor here, the I1 is the one that hits it. This one here, the I3 hits it. So you should have a current labeled for each wire between nodes. You see what I mean? So this wire here is labeled I2, so I assume it's I2 all the way through that wire. So I3 all the way through that wire and so on. The longer ones are the ones that are a little bit more confusing where the resistors are necessarily. But this whole wire here is I6. That current's flowing through that wire all the way around. And so I'm using whatever current is flowing through that resistor at that point. That's the one that I use. Are we okay with everything else using that setup? Okay. I assume you don't need me to type that in the calculator. Okay. All right. So let's do last application. And I'm guessing many of you have seen this application as well. We're going to do some chemical reactions. Now, you might have, I've in the past had people, where in the world is my piece of paper that has the chemical equation? Oh, there it is. I've had people say, well, I know that this is true because I know this particular type of reaction. Yeah, no, I'm just going to set up the equations, okay? If you know a faster way to do this, great, okay? I'm not a chemist. I'm just trying to give you some applications of how linear algebra is used other places, especially for systems of equations. All right, so let's look at the first one here, and we're just going to talk about how we set it up. That's all of how we set it up, how we get the solution, and then how we'll interpret the solution at the end. I know that many of you have had chemistry classes and know how to do this. Okay. Oh, sorry.
Do you want to push it?
Yeah, I prefer not to have my kidneys smacked. Thank you. Appreciate that. All right, so we've got this chemical reaction, and we want things to balance, right? Whatever number of atoms you have over here has to be the same number of atoms you have over here. All right, so what I need to know is how many molecules of this one, this one, this one, and this one. So I've got 4 variables to solve for, right? And again, all the atoms have to match up at the end. So I'm going to write down this chemical equation here and switch over back to my laptop here in a second. All right. So there's the chemical equation that we started with. I need to know again how many atoms of each type do we need, or excuse me, the number of molecules of each type that we need, making sure that we keep the number of atoms the same on both sides. Okay, we can't gain or lose atoms as we go across. So let me just call this X1, X2, X3, X4 as we go across. And then we just start going across the different types of atoms that we have and set up our equations. Okay, so notice we've got carbon atoms, oxygen atoms, hydrogen atoms. So everything has to be the same for a number of atoms. So if I look at carbon atoms to start with, if I assume I have X1 of the carbon dioxide, no, that's not carbon dioxide, I was looking at the wrong one. Whatever CH4 is, I don't know the name for that one. Well, thank you. Methane? Sweet. Great. Wonderful. Learned something new today. I read the right one. That was what I read, was the carbon dioxide. That one I know. I also know the other one's water. See? I know things. You gotta remember the last chemistry class I had was at junior in high school. So that was where my chemistry knowledge ended. Okay. So I didn't know that was methane. Anyway, great. Fantastic. How many carbon atoms do you see on the left-hand side if there's X1 molecules of methane? Well, we have X1 molecules, so it'll be X1, yeah. Right? On the right-hand side, how many do you have? X3, yeah. So X1 has to equal X3. On the left-hand side, how many hydrogen atoms do you have? 4x1, good. How many hydrogen atoms do you have on the right-hand side? 2x4, good. Those have to be equal, right? We can't gain or lose atoms, so they have to be the same on both sides. Okay? Finally, how many oxygen atoms do you have on the left-hand side? 2x2. On the right-hand side? Good. Those all have to be equal. There's our system of equations to solve. Now, we'll have a little bit of a nuance here at the end, because again, these are atoms. So what type of numbers would you expect X1, X2, X3, X4 to be? Whole numbers, right? So we're gonna get, notice that this is underdetermined, right? We got 3 equations and 4 unknowns, so we'll get infinitely many solutions. But we'll pick a solution where that'll work with whole numbers. And we'll see where that comes up at the end here. All right. So if we put everything in standard form here, or at least in a form that we can write our matrix, we've got x1 minus x3 equals 0, 4x1 minus 2x4 equals 0, 2x2 minus 2x3 minus x4 equals 0. So from here, we should be able to create our augmented matrix. What does our augmented What does our augmented matrix look like? There's 4 and 0. Yep, good. There's 4 variables, right? So 1, 0, negative 1, 0, and then a 0 on the end. The next one. Good. Last one. Good. We okay with getting that set up? Again, notice that we have zeros here. What type of a system do we have if we have all zeros for our constant? What do we call that again? Yeah, homogeneous, yeah. Oh, I know homogeneous is what they say in chemistry. We say homogeneous in math. Same thing. Okay. All right. So actually, as long as you understand that these are all zeros, do you think it's even necessary to type this part into your calculator? No. Because if I do row operations with these zeros, I'm still going to get zeros there, right? So if you're comfortable with understanding that there's a column of zeros there, you really only need to type in this part of your calculator and row reduce. I mean, it doesn't hurt to type it in. It's not going to change anything. I'm just saying that you don't have to type it in if you don't want to. Okay. All right. So go back over to calculator. What's that?
The WebAssign had something like that.
Oh, yeah.
Just didn't fill out the.
Yeah, it just didn't fill out the last thing. Yep. All right, so I'm just going to do the same thing. I'm going to make it 3 by 4. 1, 0, 0. Negative 1 is already there. 0 is there. 4, 0, 0, negative 2. 0, 2, negative 2, negative 1. Again, it does not hurt if you put the column of zeros in there. It's just not necessary because you already know there's a column of zeros there. And it'll stay a column of zeros no matter how many row operations you do. Okay. Quit. Reduce row echelon form. And let's make it a fraction. I will put just to illustrate what's going on, I will put the column of zeros back in on the screen here in a second. Is that what people got when they put it in? Okay. All right. So I put the column of zeros back in just so that we can see the equal sign. Notice that x4 is free. And we should be able to write x1, x2, and x3 in terms of x4. If x4 is t, what's x1 in terms of t? A half t. x2 is t, yep, because everything's going over to the other side, right? All the signs are getting flipped. x3 will be 1/2 t. So again, we get infinitely many solutions, which actually the infinitely many solution parts make sense, right? You can have any number of molecules that you want on both sides of the equation. So the fact that you have infinitely many solutions makes sense. We just want to make sure that we get integer solutions, right? We don't want fractions. So what would be a good value to plug in for t so that all of your fractions go away? 2, yeah. So if t is 2, then we get the equation what? We get CH4 plus O2 2O2 equals what? CO2, I can put these in correctly. Sorry, I did that back. Yeah, that's right. CO2 plus 2H2O. I put in 2 for T. It was a 1/2 T. Right? And I put the T in for T, I get 1 for X1. So I get CH4. I get 2O2 and 2CO2 plus 2H2O. Or CO2 plus 2H2O. That's a C. Okay. Or I shouldn't use an equal. I should have used an arrow. I know. I do know that from now in chemical equations back in high school. But you can always set it up with a system of equations. And I know that there are methods. Like I said, I've been yelled at it enough by chemistry students. I know there are other ways that you can do things quickly. Okay? to show you how you can set up a system of equations and then pick out an integral solution that works. But again, if I multiply any of those now by any integer that I want, this would work, right? I can multiply both sides by 2 and I still get a balanced equation. And somehow, in some sense, we're doing something that's in lowest terms, like fractions, right? We just divide out a greatest common factor. But we can always deal with a system of equations. So anyway, have a good one. We will see you whatever day that is, Friday. Today's Wednesday, right? Yeah. Okay. See you on Friday. Have a good one. Yes.
Since it's a problem like